Imagine watching a metal cutter spinning so fast it looks completely still, then, within seconds, a solid block of steel transforms into a perfectly machined part. No smoke. No struggle. Just smooth, lightning fast cuts. It almost looks impossible. So here's the question: how can a machine remove more material, produce a better surface finish, and sometimes even make the cutting tool last longer, all by spinning faster? Today, we are uncovering the science behind high-speed machining and why it's changing modern manufacturing. Mirroring. If you've ever seen videos of CNC machines throwing chips everywhere at unbelievable speeds, you've probably wondered, wouldn't spinning faster destroy the cutting tool? Or maybe you've heard machinists say that high RPM equals high wear. It sounds logical. But here's where many people get surprised. High-speed machining isn't simply increasing spindle speed. It's a carefully balanced combination of spindle RPM, feed rate, cutting strategy, tool design, machine rigidity, and cooling. When all these factors work together, the results can be incredible. The landscape of modern manufacturing, efficiency, and precision are no longer competing priorities, they are simultaneous demands. For decades, conventional machining relied on a brute force philosophy, heavy cutting depths, rigid work holding, and slow, deliberate feed rates that plowed cutting tools through raw stock. While reliable, this approach inherently generates massive cutting forces and intense thermal energy, both of which degrade tools and warp workpieces. High-speed machining, HSM, fundamentally flips this paradigm, shifting the operational focus from heavy material removal to highly rapid, optimized cutting dynamics. At its core, HSM is defined by operating at spindle speeds and feed rates significantly higher than traditional thresholds, often exceeding 10,000 to 20,000 RPM depending on the material. Rather than forcing a cutter to take deep, stressful cuts, HSM utilizes a strategy of low radial depth and high axial speed, or vice versa. The 0.005 mm nightmare. One tiny mistake. That's all it takes. Not a broken tool. Not a machine crash. Not even bad material. Just a few microns off, and suddenly the entire part is scrapped. If you've ever worked on tight tolerance machining, you already know the pressure. Your hands start sweating before the probe even touches the part. You check offsets again. Then again. Then once more before pressing cycle start. Because when tolerances go below 0.01 mm, there's no room for guessing. And the worst part. Most machinists are taught basic machining, but almost nobody teaches the real-world tricks professionals use to hold micron-level accuracy consistently. That's why some shops produce aerospace-quality parts every single day, while others struggle to keep dimensions stable for even one setup. Today, we are breaking down the micron-level machining secrets professionals use to hold insanely tight tolerances without wasting tools, time, or expensive material. And one of these tips alone could completely change your machining accuracy forever. Why tight tolerances fail? Most beginners think tight tolerance problems come from the machine. But professionals know something important: the machine is usually not the main problem. The real enemy is variation. Tiny variation. Invisible variation. The kind you can't even notice until inspection fails. Heat expansion. Tool deflection. Improper work holding. Worn inserts. Coolant inconsistency. Even touching the part with warm hands can affect measurements at micron level. That's what makes precision machining different from normal machining. At standard tolerances, mistakes hide. At micron level, everything gets exposed.